Hello and welcome to the tutorial of the DSS.WSET-DC model, a decision support system for the optimization and expansion of water supply systems in developing countries. My name is Carolina and the model was developed as part of my master's thesis. Its purpose is helping decision makers during the project stage of strategic planning. The tool is tailored for urban and peri-urban areas in developing countries. It can be applied to cases with both existing infrastructure and areas where a new formal water supply system needs to be planned from scratch. The model guides the user through three main phases, which structure the entire planning exercise. Phase 1 focuses on characterizing the current system, with the user defining the project zones, their attributes, connections, abstractions, and treatment levels. Phase 2 performs system optimization, proposing optimal water abstractions and treatment levels, identifies viable distribution models for each zone, and generates all feasible alternatives. Phase 3 focuses on the evaluation and ranking of all alternatives. Each option is assessed against 16 technical, social, economic, and environmental criteria. Criteria weights are defined externally with the participation of stakeholders through a questionnaire developed in the context of this model. The evaluation is founded on the model's database, which defines individual scores, lifespans, and costs. The database is editable and highly adaptable to each specific project. The model aggregates all scores, producing a global ranking. The model is fully implemented in Microsoft Excel using Visual Basic for applications. A complete instructions guide was also developed, as well as the questionnaire to define the criteria weights, and both are available. You can download it below in the description. Regarding the computational tool, it is source available with access granted upon request. In this video, I will walk through the key components of the model interface, showing how the three phases unfold in practice, based on two practical examples. By the end, you should have a clear understanding of how the DSS.WSET-DC model can support planning exercises and helps compare different alternatives in a structured way. With this said, let's now move to the model's interface and begin its demonstration with phase 1. Okay, so here we have it. We are in Initial Diagnostic 1, which is the first sheet of phase 1, which actually encompasses these three sheets up to current situation. The first two are for inputs, and then the last one is for visualizing the information you have provided and to generate a visual diagram of the existing water supply system. You will always find in each sheet the instructions which will help you in the process of introducing the inputs and in running your procedures in order to get the best results. So here in Initial Diagnostic 1, we first have some general data on the project area and zones, and then some more specific one on the abstractions. The water abstraction can or not be centralized. In this case, it is not, reason for which we have more than one. So actually we have here zones 2, 6, and 5 as already being supplied and as being directly connected to the abstraction. So, and I brought here this simple scheme in order to better explain and illustrate the zone categorization that is done according to the connection types. So these three zones, they are directly supplied by the abstraction. So this means they are root zones, existing root zones in this case. The other ones, they have not yet specified connection type, so they will fall into one of the other categories, and that is done in Initial Diagnostic 2. So here in this first part, which is code generated, you can see here that the zones are already classified as roots or not roots, and the abstractions they are supplied by. Then you have to input some data on zones for all of them very carefully. And I want to pay special attention here to this section where we say for each zone we already have a formal water supply system, and in case we do, we specify some data on it, and then we define the connections existing or future ones for the zones that have not a specified connection yet. So if we look first here at zone 3, it is not a root zone, but we say it already has a formal water distribution model. This means that it is part of the current water supply system. If it's not a root zone, this means that it gets its water from an abstraction. In this case, we do not have only one, we have more, but it gets its water from an abstraction through another zone. So this will fall into the leaf zone, existing leaf zone in this case, category. And actually, this is the only option. So upstream zone, it connects to an upstream zone, an existing connection. So in this case, zone 6, but here all root zones appear. For the other two, we have not classified them as root zones, and here we say they are not yet supplied formally. So they do not yet connect to the water supply system of the project area, which means that they will only connect in the future, and for that we have projected connections and we have other options. So if they connect in the future to an upstream zone, that means that they will fall into the projected leaf category. If in the future their projected connection is to an existing or a new abstraction, then they will fall into the projected root zone. They will connect directly to an abstraction. But in case, which can happen, we have not yet defined the future connection for this zone, which is not yet supplied, then we just say it is not defined and it will fall into the free zone category, meaning that it will still have to be evaluated how it will connect to the water supply system we are setting in place. So here for the existing source, of course, all existing sources appear here, existing abstractions. With all this defined, here we have defined the connection types according to these ones for all zones, and then we go to current situation, where we can see all our inputs. Also, we can see here the zone type classification according to the data we have provided. And if we check everything is correct, we just create the existing system diagram, which is done according to which shows the existing connections and is done according to the zone type classification that we have defined. If, let's say, this was also not yet defined, that would change there, and automatically as we ran the procedure here. That is not the case, so it will connect to abstraction 2, and that is what we see. So this finishes phase 1. We already have an established current water supply system, and from now we move on to the second phase, where we'll do optimizations, we'll generate viable distribution models, and we will create the alternatives to ultimately be evaluated in phase 3. Phase 2 starts with the evaluation of all abstractions, either existing ones or new ones, which in this case we will evaluate 2 new possible abstractions that could supply the zones, and we will evaluate all of them against all of the eligible zones. So again, you have here the instructions which specify the steps you should take and the criteria that is used in order to get the ranks, the abstraction ranks for each zone. So I will not be getting into that detail, but I would just like to note that the evaluation assumes that the abstractions have the required capacity to supply all zones. So that should be taken into account when you select the abstractions that you will be using in your project area. And also that here you have some predefined values that the model uses in order to define the rankings. But if you do not want to use these, then you should provide values here in this table. Okay, so now I will run the first 2 procedures and I will be right back with the results. Okay, so I have just ran the first 2 procedures. Here first we get the zones for which the evaluation will be performed. You can see that only root and free zones are evaluated. This because leaf zones are not directly connected to an abstraction. And for each of these zones, all abstractions, new and existing, are evaluated for each. In this table, after running the abstraction evaluation procedure, you get calculated distances and flow types for all abstractions, and you have in this last section the first ranked abstraction for each zone. If you want, you can consult this more complete report, which gives you the full rankings for each alternatives and its characteristics. This table here serves the purpose of overriding results if needed. So let's say that for zone 5, I wanted to study a second abstraction. I'm sure that I want to do that. But abstraction 3, according to the program's criteria, is actually the best one. That is what the program is saying here. You should maintain the abstraction. But that is not what I want to do. So I said zone 5. So I can here override the results, I update, and then I am shown the following 3 top alternatives. So in this case, abstraction 1 and C2 and then C1. But that is not the case, so I'm going back to maintain, and then I just create the optimized system diagram. With this, we have defined connections for all our root zones, either existing or new ones. You can see that all of them are connecting to the water supply system, and in this case is not the existing one, but the future one that we will be evaluating. You can see too that our zone 4, which was a free zone, and will actually be evaluated both as root and as a leaf, because we did not define what type of connection we need. So both types will be evaluated. For when it is evaluated as a root zone, it has already been attributed an abstraction. So with this done, we are ready to proceed to the next step, which is the treatment optimization, the second step within phase 2. We are taken to this sheet where the minimum adequate treatment will be selected for each abstraction entering the next phases. We can see that even though we were studying 5, we were studying NC2, it was not selected for any abstraction, for any zone. So when we come to treatment selection, no treatment is defined for it. So on this sheet, again, you have instructions. You have here flow diagrams that specify how the evaluation is performed. So I will not be getting into that detail. I will just fill in the data and I will be back with results. Okay, so I have already filled in the data. So I have where in the cases where we have numerical parameters, a numerical evaluation is done. If we do not, then the visual evaluation will be performed. So then we just need to calculate the minimum adequate treatment. And I just want to point out that if we can see here, abstraction 3 already has a treatment in place. And even though we have data that, as we can see here, the numerical data indicates that just disinfection is eligible, is the minimum adequate treatment, no treatment downgrades are considered conservatively, so filtration plus disinfection remains as the treatment for abstraction 3. I also want to note that for when we do not have numerical parameters and we perform the visual evaluation, the minimum adequate treatment that can be defined is filtration plus disinfection. So also conservatively, just disinfection is not eligible when we are doing a visual evaluation. So at this point, we have already defined the current water supply system. We have defined for the new zones and also for the existing ones, when it's the case, an abstraction optimization. And now we will define the viable distribution models for each zone. For that, we come here to this sheet, which again has all the criteria, so I will not be getting into much detail into how the program selects the viable distribution models for each zone. I will just start by running this first procedure, which fills in this table with already the transmission types that we defined for the zones that are already supplied. And we can define the existing distribution model for each of them. We can specify the model that already exists. This is an academic exercise, so I will actually just choose whatever. But I just want to note that according to the transmission type, we have different options. So if it's piped, we have this, and if it's water tanker, we have others, as they correspond to different numbers in the models, distribution models catalog. So now we'll just generate a distribution model report, which shows us the viable distribution models for each zone, and I will be back. Okay, so we already have the results, and I want to note that for zones 2, 3, 5, and 6, which are our existing roots and leaves, we have defined the distribution model, which corresponds in the catalog to these numbers, and they are here. And for those, there are no other viable distribution models suggested. This happens because the model does not create automatic optimizations. It only suggests viable distribution models for the zones that are not yet served. The second thing that I want to note is that our free zone, zone 4, here is evaluated both as root and as leaf. And for the case it is a root, we have defined its abstraction, but for when it is evaluated as a leaf zone, the root zone it connects to is defined in this phase of the project according to its to the procedures criteria. And so here we already have the zone, the root zone that supplies zone 4 when it is evaluated as a leaf zone, and also the distance calculated between them. Okay, so with this, we already have our viable distribution models. For each abstraction, we have the treatment selected as well. We have all connections defined. And to complete the second phase, now we just need to generate the alternatives. But before that, we need to run this procedure to generate the full summary, which gathers all the information that has been provided and calculated up to this point. I want to note that our zone 4, which is our free zone, has two dedicated columns, and this always happens as we have evaluation both as root and as leaf, and for that different informations exist. So one has an abstraction, another has an upstream root zone. The viable distribution models are always the same, but then, for example, there is a distance to the abstraction and there is a distance to the upstream zone. These, of course, are different. And then here, this part always has to be filled in, as this information is very important for the following steps. You can see that for the projected zones, so in this case zones 4 and 1, we do not define percentage of population served, neither the existing infrastructure's age. This water consumption is, these are predefined values, and if you have information on the existing water consumptions in each zone, you should provide that as well. So not only this green part is of the report is editable, actually the whole table is editable. And to show why that is pertinent, I will actually move on to another example from now on, which is an actual case study, and we'll actually follow the rest of the demonstration with that example. Okay, so we already have here the second example. I have already ran the procedures from phase 1 and from phase 2 up to full summary, which is the sheet where we are at, and that is already completed. So I brought here the map from this case study, where we can see we have the abstraction here represented by the triangle. Then this is the existing transmission that is already constructed that goes to this pink zone, which is zone 1, our existing root zone. And from here, we have the water is supplied to the other zones, zones 2, 3, and 4, which in this case are existing leaf zones. So that is what we have already fed the program and what is represented here. They already have their distribution models. And then we have two new zones, zones 5 and 6, which do not currently have an existing formal water supply system. And for that reason, we want to expand into these areas. And we have in the distribution option 5 sheet defined the viable distribution models for each of them. As you can see, for the currently supplied zones, no other viable distribution models are suggested. I want to note that we have here these distances which are calculated from centroid to centroid. So I will illustrate. For example, here between source and zone 1, as this is our root zone, okay, this 11.4 kilometers, it's this distance. But we already have a transmission and we know its length. And this distance is actually used, for example, to calculate the operational costs regarding this transmission. So if we have an accurate data, we should use it. Then we have, for example, this 2.99 is the distance between zone 1 and the centroid of zone 3. Okay, and then the same applies to all cases. For zones 5 and 6, as we are saying they are root zones, this distance is calculated between the centroid of the abstraction and each of zones 5 and 6. But the thing is, in this specific case study, we have here this main storage, which is a global storage for the whole town. It supplies the whole town. This is 14,000 cubic meters. And the additional transmission that we will want to construct, or in the case, for example, of a water tanker, the distances that will need to be to be done is between this storage and these zones. Okay, between this storage and the centroid and the storage and the centroid, not this whole distance. So what I want to show is that to better represent our case study, we may need to alter this data. Actually, we will also introduce an optimization because zone 4 has a very low percentage of population served. So we do want to study other distribution models. Now I will be filling in all the missing data. I will also be doing the necessary changes and I will be back with all this completed. Okay, so here we have it. As you can see, for example, this distance has changed. It was 11 point something kilometers, now 14.7 because it's the true length of the transmission. We know it, so we can put it in. This distance has changed as well. As I said, we are now to zone 6 calculating just this distance, 1.61, and this for zone 5, okay? These distances, so between the root zone and the leaf zone, have also changed because what we actually want to simulate is the zone directly, the connection directly to zone 4 from zone 1 and to zone 2. But between zones 2 and 3, this is what we want to do because this is the additional transmission that we will be using that needs to be used for calculations, not this. Okay? As I pointed out, the percentage of population currently served in zone 4 is very low, 2.7, and for that reason, we do want to study other distribution models, and we apply the criteria, the same criteria that is used in the viable distribution model generation here, and just introduced the results. And we know the existing transmission age, so we also introduced that as well. From now on, to finish the second phase, we just need to generate the alternatives. And for that, the code relies solely on the full summary sheet and the code contained in it. So the way the alternatives are generated by the code is through the mathematical combination of the viable distribution models for each zone. So here we have one on in each, 4 here, and 8 for zone 5 and 8 for zone 6. So the code will combine make all possible combinations to generate the alternatives. For the user, generating the alternatives is very easy. We just have to come here and click this button to run the procedure. So I will do that and come back with the results. So we already have here the results. The alternative sheet has been generated, listing all the alternatives and the specifications for each zone, including the abstractions, treatments, upstream zones in the leaf zone cases, and the distribution models for each alternative, which, as you can see, changes according to all the combinations. So from this point on, we start phase 3, which relies solely on the alternatives database and full summary sheets. And before moving on to the demonstration of the last phase, I will quickly present the database. So here on this section, we can view the criteria. We have 4 different groups: technical, social, economic, and environmental. And what the third phase consists in is in the individual evaluation of each of those, and then on its aggregation according to these criterion rates. So if, for example, I ran the generate criterion 10 sheet procedure, I will be getting the results for equity. The equity criteria results for all alternatives. If I run the generate criterion 14 sheet procedure, I will be getting the results for the OPEX, the operational costs, for all alternatives. And the results may be presented in the 0 to 100 scale or in other local scales. Also in this database, we have tables for each model component, which are the in-zone distributions, the abstractions, treatments, and transmissions. And for each of these, we have scores, and we have lifespans, and in case of the in-zone distribution models, we also have costs. So for the other components, the costs are calculated within the criterion evaluation, but for these, they come here from the database, and they are calculated per inhabitant. What happens here is that this database is editable. For example, in the case of the costs, these are specific to this project, because this, for example, is for Sub-Saharan Africa and Angola, and this is what this is based on. And you may want to adapt it to your project. So the database is editable, and for example, for the criterion weights, these are project specific. You should always calculate the criterion for each project, so you will always have to, prior to phase 3, come to the database and at least insert the criterion weights for your specific project. So with this said, I will now generate all the procedures. Everything is separate, because even though for the user is just clicking for running the procedures, this code is very heavy. This is the most complex part of the model, so it needs to be disaggregated. So I will be doing this, and I will get back with the results with sheets for all criterion evaluations. Okay, so I have already ran all procedures and have the results for phase 3 and consequently the model's application. I have individual sheets for each criterion and also the evaluation, final evaluation, where all the results are aggregated, and the ranking. But I want to start with just quickly showing some specifications here of criteria. As I previously said, we have different scales. The final evaluation scale is 0 to 100. So we have some criteria that does not need to be normalized and others that do. So I will show some examples. So here for criterion 1, which is coverage, we can see that we only have a final score for the whole alternative that is attributed directly. For example, criterion 12, we have a score that is attributed to each zone, which is then aggregated into an alternative score and then normalized into the 0 to 100 scale. As you can see here, 12 is in the scale 1 to 4. Then we have, for example, criterion 14, which is one of the costs criteria, where we get costs for each alternative per component. So we have for the abstraction, the treatment, for the transmission and distribution within each zone, and then the general operational costs, and the same for investment costs. So each, and then of course, these costs are normalized also into the 0 to 100 scale. Then the last procedure, the evaluation sheet, also generates the ranking. So this just gets the final scores, the final normalized scores of each criterion for all alternatives, and with the criteria weights defined by the user in the database, as I have shown previously, this calculates the final scores. And then we simply are presented the ranking where the alternatives are sorted highest to lowest final score, and we get our model application result, the top 3 ranking alternatives. Even though future versions of the model are intended to include additional data visualization and analysis features, they are not automated in the tool at this stage. However, all the results are clearly displayed and can easily be extracted and analyzed. So, thank you very much for watching, and I hope this tutorial helps you make the most of the DSS.WS at DC model.